Welcome to chapter 25. We'll be dividing this chapter up into multiple videos. So this is video 1. We are starting out with geometric optics. Optics is wonderful. We've said that light acts like a wave, but one of the really cool aspects of it is we can represent the properties of light in diagrams, and they're really accurate. We can draw them using rulers and come up with accurate representations of what we would observe in the lab. This ability to describe light as traveling in a straight line, and especially to use it in diagrams, is something that we refer to as the ray model of light. So when your brain looks at light, your brain processes the information as if light travels in a straight line. And it doesn't matter if the light actually bends, your mind says, no, it goes in a straight line. This is the reason that we see some optical illusions. If you are standing in a swimming pool and you look down at your feet look much closer to the surface than they really are. This is an optical illusion because the light bends as it goes from water into air, but your mind traces it back in a straight line, ignores the bending, and says, aha, the light is really here. And so this ability to make our images follow these straight line paths create some interesting effects. So in our diagrams, we're going to, whoops, I'm sorry, I overshot. In our diagrams, we are going to treat light as if it's a ray or a vector. So we'll use a ruler and we will form images at points of intersection, which is the way your brain processes the light. So we will start out by looking at some of these diagrams. So we'll start out talking about a plane mirror. That means it's a flat surface. And a flat surface follows the law of reflection. So the angle of incidence equals the angle of reflection. If this blue box is our mirror, our reflective surface, and the arrow on the left is the incoming or incident ray, when it hits the surface, it bounces off and gives us the reflected ray. In our drawings, instead of a solid red line, we would have had a dashed line, the normal to the surface. So angle of incidence is measured with that line, that dashed line that we would draw in, and it's equal to the angle of reflection. We also have some distances to describe. You have the object distance. We will symbolize it as d sub o. In old books, it was a lowercase p. This is the distance between the object and whatever optical device you're using. So whatever lens or mirror you have in place. The image distance is d sub I. In old books, it was lowercase q. And that's the distance between the image and the optical device. So again, between whatever your image is and your mirror, or whatever your image is and the lens, if that's what we're using. A real image is an image that's formed by the actual intersection of light rays, and it can be focused onto a viewing screen. We will be using viewing screens in lab, and so any image we can focus on that screen will be a real image. If it doesn't focus, it's a virtual image. Now, your brain can take information that doesn't actually focus on the retina and turn it into an image, because your brain infers what's actually there. And again, that's where these optical illusions come from. So a virtual image is an image that's formed by the imagined intersection of the rays. It is not actually focused on the retina. It is not actually focused on a viewing screen. Your brain makes this stuff up. And again, we'll have some drawings that I hope will make this clear. So for a plane mirror, We might want to shrink our drawing down just a tad, just to make it a little easier to see. So for a plain mirror, a flat mirror, that's what this image is all about. For a plain mirror, if you are the object over here, you have light from your foot hitting the mirror and bouncing off, and your eye sees it, but your eye traces it back in a straight line and says, aha, my foot is over there. You have light from your head hitting the mirror and bouncing back and hitting your eye, and you trace it back in a straight line and you say, aha, my head is over here, so I must be this guy in the image. That's how we perceive it. This is a virtual image. I guess now is as good a time as any to talk about that. The image is a virtual image. If this is a mirror and you put a viewing screen on the back side of your mirror, you will not focus an image. You and I know that to see anything in a mirror, you have to stand in front of it. So anything that comes to an apparent focus behind the mirror is a virtual image. There is no real light back there. Your mind is just making it up. It's pretending. We're going to talk about spherical mirrors, and we will do a lab on this. So a spherical mirror is a curved mirror. If you want to think of it, it could be a slice off of a mirrored ball. So you've got a mirrored ball. At a mirrored ball, there's the center called the center of curvature. That's the center of the sphere. The radius of curvature is the radius of your ball. And the focal length is actually half the radius. The focal length is actually half the radius. So if you had one of those gazing balls in your garden and you were looking at the outside of it, the diameter of the ball divided by 2 would give you the radius, and the radius divided by 2 would give you the focal length of that curved outside part that you were using as a mirror. So the focal point is the point on our principal axis, on the horizontal axis, where light rays that come in parallel to the axis would come to a focus. The focal length is the distance between that focal point and the actual mirror itself. And we've already said that the focal length is the radius divided by 2 for that curved surface. Sometimes when you look at an image, it's larger or smaller than it is in reality, and that is the magnification. So magnification is equal to HI over HO, or sometimes we say M is equal to hi-ho, just like in the cartoons. So HI over HO, but it is also equal to minus DI over DO. So the magnification is equal to H is the image height, HI is the image height, HO is the object height. HI is the image height, HO is the object height, DI is the image height, DO is the object. DI is the image distance, DO is the object distance. And this minus sign is really important. If your image is upside down, if it looks inverted, its height would be a negative value. So upside down images have negative magnifications, right side up images have positive magnifications. Lens or mirror equation, we'll use these these 3 equations we will use a lot. You're going to need to know all 3 of them. So the lens or mirror equation is that 1 over F equals 1 over DO plus 1 over DI. And it doesn't matter in this equation whether DI is first or second. It does in the magnification equation. So positive numbers for DI and DO are on the observer's side of the mirror. For image distance. Positive image distances are on the observer's side and can actually come into a focus. Negative ones are on the opposite side and cannot. And we'll do numerous examples. So let's look at our converging mirrors. We're going to do this in lab. A converging mirror is a concave mirror. So if you looked at a spoon, if you looked into the bowl of the spoon, into the cupped part of a spoon, you are looking into a concave mirror. So a concave mirror, or if you took a mirrored ball and you broke it open and you looked inside, not from the outside, but inside, that's also a concave mirror or a converging mirror. They have positive focal length, so their F values will be a positive number. They have positive object distance. To use our equation, all of our object distances are positive. The image distance for a converging mirror is going to vary. It depends on, are you standing really close to it or far away? If you're standing close, you'll get one kind of image. If you're looking at yourself at a distance, you'll get a different image. So not only will it switch between being real and virtual depending on how close or far away you are, it's going to switch between being right side up, that would be erect, and upside down, that would be inverted. And the observer, that's you, is always on the real side or the positive side of our mirror. So rules for my ray diagrams will be that any ray that comes in parallel to that central axis is going to go out through the focal point. It'll hit our mirror, bounce off, and come out through the focal point. Anything that comes in through our focal point will hit the mirror and bounce out parallel to that central axis. And anything that hits at 90 degrees or perpendicular to the surface is going to bounce straight back and come through what is called the center of curvature. And we will have some diagrams. We'll practice these in class and in lab. So let's look. If this pink represents our concave mirror, and the object is over here, and you as the observer are over here on the far left-hand side looking. So light that starts out at the top of the object comes in. This black line is our central axis. So light that starts out at the top comes in, hits the mirror, bounces off, and goes out through the focal point, F. Light that comes in through the focal point, hits the mirror, and bounces off parallel to the axis. And where these two cross each other, that's the image. So you're over here and you're looking and you see this ray, and your mind traces them back until they cross. They cross right here. And that means that's where the top of the object is, because both those rays started out at the top of the object. So the top of the object is right here, and we would draw our image looking like this. So you can see that our image is upside down. It is inverted. It is real because these light rays really do cross there. And another thing we notice about it is it's reduced in size. If you look at this little arrow that we've drawn, it is much smaller than the object. So if our image is smaller than the object, it is reduced. So we know three things about this. It is reduced, it is inverted, and it is real. And again, we'll work on this in lab with drawings. So I think we will save the drawings till class, but we'll come in parallel and out through the focal point. We'll come in through the focal point and out parallel, and our image will be in here someplace. So I think we'll draw these images in class, and we'll have some more practice in lab. If you want to do them ahead of time, you can look at the previous example for the in parallel, out through the focal point, in through the focal point, out parallel. I would only draw 2 rays. Don't ever draw the third one. You can't get 3 lines to cross each other. You have to be very precise to get that to work. So if you want to practice, go ahead, but we will do these physically in class. Some uses for these kinds of mirrors would be for magnifying mirrors. I know I have a magnifying mirror in my bathroom. If you want to try this out, you can take a spoon and hold it really close to your face and look at yourself in the spoon, and then hold it away maybe at a distance and look at yourself and see what kind of images you see. Spotlights use these kind of mirrored surfaces. If we examine them, in a spotlight, if you put the light at the focal point, it comes in from the focal point and then out parallel. So any light that originates at the focal point will hit the mirror and come out parallel to that central axis. And that's what we want our spotlight to do, have a narrow beam of light. So again, we'll draw the rays that go with these diagrams in class, and we'll have some more to practice in lab. A diverging mirror is a mirror that spreads light out. Converging mirrors bring it to a focus. Diverging mirrors spread it out. So a diverging mirror is a convex mirror. Thinking back to that gazing ball, it is, if you leave the ball intact, a mirrored ball, if you look at yourself on the outside of it, that's a diverging mirror. If you take that spoon we used in the previous examples and you turn it around, and instead of looking into the bowl, if you flip it to look at the back of the spoon, that's a convex surface. It bulges out. So convex surfaces have negative focal lengths. Again, the object distance is always positive because you have to stand in front of the mirror to look into the mirror to have it be seen. The image distance is always going to be negative. The image is always going to be virtual. The image is always going to be positive. So that means it's always erect. Diverging mirrors always have virtual, erect, and reduced images. And again, we'll practice drawing them in class and in lab. So what are our rules? In parallel, out, notice the words are as if. It doesn't actually pass through the focal point, it just acts like it does. So in parallel, out as if from the focal point, and then in perpendicular to the surface, out straight back through the center of curvature. And see, the center of curvature is over here. So we'll have a ray coming from here all the way through, passing through C. It'll be solid on the left side of the mirror and only dashed on the back side. Rays that you draw on the non-real side, on the non-object side, have to be dashed. So in parallel, out as if through the focal point, it'll shoot out at some angle, but on this side of it, we'll draw it as a dashed line. And again, they're all erect, virtual, and reduced. Look at the back of the mirror. Some uses for these. Well, the mirrors you see in like convenience stores are these kinds of mirrors, the ones they have stuck up in the corner to give them a wide angle view of what's going on. The wide angle mirrors that you sometimes see on trucks are shaped like this, or you can even buy them to stick on your outside mirrors on your car if you want to. So let's look at some of our equations. Let's solve some problems using these curved mirrors. So suppose we have a concave mirror and it has a radius of curvature of 2 meters. The object is placed 0.75 meters in front of it. Where is the image and what's its magnification? So concave means it has a positive focal length. You need to know that. They told us that the radius was 2 meters. The object is 0.75 meters in front, so DO is 0.75 meters. We want to know where is the image, that's DI, and what is the magnification. And we have our three formulas that you need to know. The first thing we're going to do is find the focal length. We know the radius. If every time you have R, you need to find F. We need F for our equations, and so we need the focal length. So to find the focal length, we say F is equal to R divided by 2. So 2 meters divided by 2 gives me 1 meter. My focal length is 1 meter. If we know F and we know DO, we can find DI. And once we know DI and DO, we can find the magnification. So we need to find the image distance. That will be our second step. We're going to find our image distance. So we know that 1 over F is equal to 1 over DO plus 1 over DI. So 1 divided by the 1 meter equals 1 over 0.75 meters plus 1 over DI. 1 divided by 1 meter, 1 over 1 is just 1, and the units would be meters to the minus 1. It is okay to leave that out because we know if we start out with meters for our distances, we're going to end up with meters. And so after the first step where you plug in the units, we don't need the units again until the answer. So 1 divided by 1 gives us 1. 1 divided by 0.75 gives me 1.33333333. So I kept a few digits, but not all. And we've still got the 1 over DI. So what will we do? We're going to take and subtract the 1.33 from both sides. So 1 minus 1.333 equals 1 over, oh, that's the wrong way. It's not a, shouldn't be a superscript. It should be a subscript. Oh no, there's a mistake. I apologize. Wrong thing got in. Should be a D and an I, and there we are. Now it's in the right place. So 1 meter to the minus 1 minus 1.333 gives us negative 0.333. And again, you don't have to include the units. It's perfectly okay to leave those off. To get DI, you multiply both sides by DI and divide both sides by negative 0.333. So the image distance is 1 divided by negative 0.333. And that would give me just negative 3. So the image distance is negative 3. We know it's measured in meters because all the units we started out with were meters. Image distance is negative 3 meters. By having it negative, I know it's a virtual image, which means it's on the back side of the mirror. If your image distance is negative, you have a virtual image. So now we want to find the magnification. The magnification would be, the formula is M equals minus DI over DO, which is equal to HI over HO. We don't have the heights, we have the distances. So the magnification is minus that negative 3 divided by 0.75 meters. You'll notice that a minus, so 2 negatives on the same side multiplied by each other gives us a plus, and 3 divided by 0.75 is 4. Notice the units cancel. Magnification does not have units, so it's not measured in meters. When you do the math, you need to make sure that your numerator and your denominator had the same units on them, but magnification is unitless. The magnification is positive, and what that tells me is my image is erect. It would look right side up, and my magnification is bigger than the number 1, so that tells me that I'm looking at an enlarged image. In fact, it's 4 times bigger than the actual object. So the image is erect because the magnification is positive, and the image is enlarged because the magnification is bigger than the number 1. All right, new example. We have a diverging mirror with a radius of curvature of 1.5 meters. The image is 0.5 meters behind the mirror. Where's the object and what's its magnification? So known, we know that it's a diverging mirror. That means it has a negative focal length. You need to write that down or you'll forget. it is things that are diverging. Well, immediately, if you tell me I have a diverging mirror, I know it's a negative focal length, I know it's a virtual image, and I know it's going to be erect and reduced. So let's see what those numbers turn out to be. They said, where is the object? So we need to find D sub O. And what's its magnification? We need to find M, and we have our 3 equations. Oh, I overshot. I apologize. So we have that, and we can plug in. We know that, whoops, there we are. We know that the image distance is negative 0.5 meters because they told us it was behind the mirror. So behind means it's negative. First thing we want to do is find F. Why? Because they gave us R. So F is equal to R divided by 2. 1.5 meters divided by 2 is 0.75 meters. That part's easy. But we have to put in the minus sign. Don't forget the minus sign. That's why we wrote it down in our list of knowns so we wouldn't forget. So the focal length is negative 0.75 meters. Now what we need to do is find the object distance. So we've got our trusty equation. We know that 1 over F is equal to 1 over DO plus 1 over DI. We need to make that just a squidge bigger. 1 over F is equal to 1 over DO plus 1 over DI. So 1 over negative 0.75 meters equals 1 over DO plus 1 over negative 0.5 meters. Well, 1 divided by 0.75 is 1.33, but we have to keep the minus sign. 1 over DO just tags along. 1 divided by 0.5 is 2. And you'll notice a plus, a minus is just a minus. And you'll also notice that I left out the units because I didn't want to type in meters to the -1. If you want to write them down, that's fine. If you want to leave them off, that's okay. Our answer will be in meters because that's what we started out with all of our numbers in. So to get rid of this 2 on the right-hand side, we have to add 2 to both sides. So negative 1.33 plus 2 will give us 1 over DO. So negative 1.33 plus 2 is positive 0.667 equals 1 over DO. To get the DO out of the denominator on the right-hand side, I multiply both sides by DO, divide both sides by 0.667, and I end up with 1.49999. If you round it off to 1.5 meters, you'd probably be okay. What does that tell me? That tells me the object is roughly 1.4999, actually it's 1.5 meters in front of the mirror. A positive object distance means you're in front of the mirror. To find the magnification, M is equal to minus DI over DO, which is HI over HO. We don't have any heights, we have distances. So that's what we'll use. So M is going to equal minus negative 0.5 meters divided by positive 1.4999, and you end up with 3. Notice that the minus makes it a plus, so we know it is erect. Oh, I'm sorry, it isn't 3. What was I thinking? It's 1/3, which is 0. There we are. My apologies. I don't know where my brain was going with that. So a minus makes it a plus. The meters cancel. The answer doesn't have units. And 0.5 divided by 1.4999 is 0.33333. So it is erect and reduced, and it is erect because the magnification is positive. It's reduced to about 1/3 the size of the object, and it is virtual. Oh, I'm sorry, it's real. Magnification is positive, so it's No, it's a virtual image. I tell you what, I'm just getting everything backwards. The image distance is negative, so it's a virtual image. With the E and because, and there we are. And this video is going to stop here. So we'll stop and we'll pick up with lenses in a different video.